Yes, okay. Good morning, I'm Ivan Carnimeo, and I'm working here in the group of Trieste, SISSA, with Stefano Baroni and Paolo Giannozzi. We are basically trying to develop some efficient scheme for the evaluation of the artifact exchange in quantum espresso. Basically, I will first show briefly how the pre-existing code is and the algorithm and how is structured. And then I would like to introduce the interprojection formalism, which I think is a general way to introduce the ACE method, which has been recently developed by Lin and which has been implemented in Quantum Espresso and is available in the last release in September in 6.0. And finally, if I have time, I would like to say something about the localization, the localization of the orbitals, which can be also used in order to make the evaluation of exchange more efficient. So basically, the problem is that we have to solve a set of Konesham equations where in the Konesham operator we have the artifact exchange term. The point is that while all the other terms depends on the density, the artifact exchange depends directly on the orbitals or on the density matrix. So the shape of the exchange potential is like this, and the problem is that we have to evaluate those integrals for every band pairs. So this makes the procedure very long to be evaluated. In practice, for every band pair, we have to first take the wave. If we want to apply the exchange operator on the, say, some function phi k, we have to take phi k from the G space and bring it to the R space because the ansatz of the wave function in plane waves is in G space. So we need to do one FFT to bring it to the real space. Then we assemble the density of the product of the two functions inside the integrals in the real space. Then we bring the density to the G space and we solve the integral in G space. Then we bring back the solution of the Poisson equation into real space. Then we increment the exchange potential and we again transform to G space. Since this procedure must be done for every band pair, it takes a lot of time and a lot of resources, so this is basically the problem. The algorithm for the SCF is something like this. So we first do one pure DFT step, so with no exchange. And the point of doing this is because when we switch on the exchange term in the potential, we want to start from a guess of orbital, which is the closest possible to the final solution. And so we prefer to start from a convergent set of orbitals convergent from a pure DFT calculation with no exchange. So this is the first step, and then we switch on the exact exchange term here. And the SCF is structured in a double loop, nested loop. So basically, starting from the convergent DFT orbitals, we assemble we have here to calculate the first exchange potential on the same set of orbitals. So here we apply the exchange operator on a pk function, which belongs to the same set which has converged. So it's the same set which we use to build the density matrix here. And this is needed to calculate the energy. And so then we make a copy of the orbital. We save it in a buffer, which is called the XX buffer. And then we start with the inner loop, in which we optimize one set of orbital by keeping the density matrix frozen. So basically, we keep the psi functions from the previous outer iteration frozen, and then we optimize the phi functions. Then once we are at convergence on the psi functions, we check convergence. And when we are at convergence, we we update the density matrix. So we use the new psi functions in order to build the new density matrix, and then we start again from here. So basically, the SCF with the exact exchange is an iterative procedure in which we start from a density matrix, we optimize the orbital, then we update the density matrix, we optimize again the orbitals. And here there is a, I think, graphical representation of the SCF. and which I have reported for ethylene with 1 CPU and 100 Rydberg, the elapsed time as a function of the SCF iteration. So we can see here, the first step is the pure DFT step, in which in this case it took 6 iterations, and these steps are relatively fast. Then at the 6th step, we are at convergence on pure DFT, and we switch on the exchange iteration. So here you can see the elapsed time, and this is related to the evaluation of the exchange term on the converged DFT wave functions. Then here we start, so this is the first outer loop call of wake 6, which is the subroutine that assembles the exchange potential. And then here we start with the inner loops, in which we optimize the phi functions with frozen density matrix. Then when we get the convergence here, we switch on again. We update the density matrix, so we have another outer loop iteration. And then we start again in optimizing the phi function with frozen density matrix. So in this SCF, we have basically 5 calls to the V86 in the outer iteration, and the inner loops took on a total of 10 iterations. We have to say that since the diagonalization procedure is made iteratively by using some Davidson algorithm, we have also to evaluate the action of the exchange operator on the residue of the Davidson algorithm. So the number of times we have to call the subroutine which makes this, the exchange potential is more than just the sum of outer and inner loop, because we need to call we need to assemble the exchange potential when we want to evaluate the energies, so in the outer and in the inner loop, but also in the diagonalization of the Consham operator. So in this case, we called that subroutine 32 times, which is more than the sum of these. So it is more than just the times that we need for evaluating the energy. So how can we, in order to trying to make this algorithm more efficient, the inner projection is a general theoretical framework which was developed by Lodin in the 70s, and it's very useful in our case, because basically, from just a very empirical point of view, it works in this way. Rather than saving the orbitals, and then every time we want to evaluate the exchange potential, we have to solve all the exchange integrals. We can rather build a projected operator which includes the action. Rather than saving the orbital, we can somewhat save the action of the operator on a set of orbitals. So every time we have to apply that operator with frozen density matrix, is just a scalar product. In more precise way, we define an operator which is on a given set of basis function with an auxiliary basis function. And then if A is the exact operator, the projection is defined like this. So by means of this auxiliary basis function, which of course, if the basis function is complete, then the expectation value of the projected and on the exact operator is the same. So how can we apply this to our exchange problem? Okay, the condition, since here we need the square root, the condition is that the operator must be positive definite. So in order to apply this to the exchange operator, we define that A is minus Vx, because Vx is negative definite. And we define as an auxiliary basis set this basis set, which is defined by means of the psi functions, which are the functions which are kept frozen in the density matrix in the inner loops. So if we just substitute, it comes that the projected operator assumes this form, and here we have the exchange matrix. Here the inner sums are implicit because I didn't want to make the notation complex. So you have to imagine that here we have a sum over I here and a sum over J here. So this is the exchange matrix, and the matrix representation of the exchange operator in the psi basis set. So as suggested by Lin, we can recover the ACE method proposed by Lin by taking the exchange matrix and Cholesky factorized the matrix. So then the projected operator can be expressed just with this vector Xi, which is defined as the action of the exchange operator on the auxiliary basis set times the Cholesky decomposition of the exchange matrix. So in order to build our projected operator, we just need to know how the exchange operator works on the auxiliary basis set, and we have to perform a vector matrix product with this matrix. We have to say this matrix is just the matrix representation of the exchange, so it's not a big matrix, it's just n band times n band, so it's feasible. So how can this be included in our SCF algorithm? Basically, here in the outer loop, we already have to calculate the action of Vx on the auxiliary basis set. So we just have to, after we have calculated the exchange potential here in the outer loop, we just have to do a left bracket with the psi function in order to have the full matrix representation of the exchange. And then we do a Cholesky decomposition, and we can assemble here now. We have the Vx times psi. We have the matrix here. We can assemble the Xi vectors. Once we have the Xi, this is not a big deal because the computational time for doing this is very small with respect to the time necessary to do this. So it's a fast step. Once we have the Xi vectors, then every time we need to calculate, to evaluate the action of the exchange operator on trial function phi, because now we are optimizing the phi functions, then it's we just need to do a scalar product, which is much faster than evaluating all those integrals. And so the same also because the evaluation of the exchange potential is just a scalar product, and also the energy can be calculated in the same way. It's very important that this can be done also in the diagonalization procedure. So if we compare here for graphical time elapse along the SCF, we see that with the if we use the ACE method, basically all the inner iteration, the cost of every inner iteration is analogous to a cost of a pure DFT iteration, because now what it was before the rate limiting step, which was the evaluation of the exchange step, now is just a scalar product. And so basically the cost is analogous to the pure DFT. Of course, in the outer iteration, the cost is the same. It's the same as with the old method, because in the outer iteration, we need to fully evaluate the action of the exchange operator on the auxiliary basis, and we cannot escape from it, because we need it in order to assemble the inner projection. So, the advantage is that in this case, rather than calling the full the subroutine which calculates the full exchange potential 32 times, we just need to do it 5 times, so only in the outer loops here. So this is a big, so the advantage is in the inner loop, so it's strictly related to the structure of the double loop of the SCF code. Okay, this is a more realistic example. This is a set of clusters of different number of water molecules. We can see that if we do this calculation for 100, a cluster of 100 water molecules, the time is 1/5. For the full SCF is 1/5 the time of a full calculation without the ACE method. So the point is now, can we further optimize? Can we do something more in order to? Okay, the ACE method is implemented. It has been released in the last in 6.0 version of Quantum ESPRESSO. It is available also for either gamma point calculation and also for extended system with K points, and also with ultra-soft pseudo potential and non-collinear spin. So it's quite. And we are still testing, and if you find that something doesn't work, just write us. But actually, it seems to be quite a stable procedure. So now we are working on, we are trying to further improve the algorithm. So the point is, can we further optimize the evaluation of the exchange? Since here, the evaluation now is very efficient and fast, the problem is, if there is something that we can do in order to evaluate those integrals. Because now this is the rate limiting step of the algorithm. So one possibility is to use, to exploit some form of localization of the orbitals. We are using this approach for the localization, which has been recently proposed by the same person who proposed the ACE method, which is Lin, and who is Lin. And it has the advantage that is a non-iterative localization procedure. And it just is a unitary rotation of the set of orbitals. So it's just algebraic. And there is no iterative functional minimization, as for example for the Vanier functions. And so it's non-iterative, and it does not require the allocation of the full density matrix. So this is, I not go through the details, but this is an algorithm which allows to localize the density matrix, but working on the rectangular matrix of the molecular orbitals. So basically, it is based on a QR factorization of the matrix, which is allocated number of grid points times number of bands, and is the matrix of the molecular orbital, so XX-BAF if in the code. So by QR decomposition of that matrix, we are able to find a set of localized molecular orbitals, which are related by just a unitary rotation from the canonical set. So basically all the physical quantities and expectation values are the same, because it's just a rotation of the occupied subspace. So we can apply our inner projection procedure to the new set, using the new set of orbitals, so using the localized orbitals. And here, in order to assemble the Xi vectors, we don't need the action of Vx on a canonical orbital, but we just need the action to know the action of Vx on a localized orbital, and then of course the matrix. So basically now, in order to evaluate the exchange potential, we have to calculate those integrals, which now involve two localized functions. The point is that the product of two canonical orbitals, on the general orbitals, appears something like this. So even on a cluster composite by water molecule, which is so with a high fragmentation, two canonical orbitals are usually spread around all the clusters. So the product is spread around all the simulation box. Otherwise, with the SCDM localization, the orbitals appear like these, like those. So the product is much more localized. And the general idea is that maybe there can exist some algorithm, some way to exploit this localization. In particular, we are thinking about two ways. The first one is that since basically the product, when we solve the exchange potential, we solve Poisson equation where the density originating the potential is just the intersection, because it's the product between two densities. So one possibility is that when the two bands are far enough, we can simply neglect that contribution in the exchange potential. Of course, this is required to define a threshold, and we are working on it in order to find a good and reproducible threshold we could think about later if you are interested. But by the way, this means that we are only including the exchange potential, the band pairs which are close enough. Otherwise, if the bands are quite distant, we can neglect it. And if you think of systems like this or even larger, that it can happen that one band is here, one band is here, so there's no point to include this interaction. The other way, which is more elaborate, would be to solve the Poisson equation rather on the full simulation box on a smaller box, which include only the localized density product. Of course, this is more elaborate because we have to think how to solve the Poisson equation on reduced box, and we have also to build to find a reproducible and stable algorithm in order to find the reduced box, which is not trivial. Otherwise, so this is still in progress. And while we have trial implementation of this method, and I can show, so basically the algorithm looks like that when we are in the outer loop, we include this localization procedure, and then we evaluate the exchange potential on the set of localized orbitals. So we build the Xi functions on the localized orbitals, but since we don't want the action, because we are doing the SEF on the Psi, not on the Psi tilde. So once we have projected the operator on the set of localized orbitals, then in order to have the true potential, we have to apply the projected operator on the psi, on the canonical orbitals. So this requires some more memory allocation because we have to allocate both the canonical and the localized orbital in VX6. So if we set a threshold and we neglect the bands that are too far enough from each other, we can see that so combining the localization with the ACE algorithm, we can see that we can further reduce the computational time, and in this case, the time for evaluating for the SEF for a cluster of 100 water molecule is about half the time required for a full ACE approach. Of course, this has a price, because we are introducing a threshold and we are deciding to arbitrarily truncate the interaction between two bands. So when we use this approach, we have that we are introducing an error in the energy, which the good thing is that the error can be set to be small enough by setting the threshold low enough. So it can be handled in some way. And if you take a good choice of the threshold, this error is quite small, because here we have at the order of 10 to the minus 3 Rydberg, and you have to think that with the 100 water molecule, the exchange energy is something like hundreds of Rydberg. So the error is really small in this case. It depends, of course, on the threshold. So I just would like to finish giving you some reference, because this is the reference loading for the inner projection theory and formalism. And then we have the two articles from which we have taken the ACE method and the localization algorithm for wave function. And thank you for your attention.
Excellent. Thank you.